Yep. Yeah, thank you for the introduction, and most of all, thank you for the invitation. Yeah, as I said, as Salvatore said, I'm at University of Padova, and yeah, today's seminar is, regards some recent works that we have done regarding optimization problems. And how to use and when to use successfully or less successfully tensor network to solve these types of problems. So I guess, it's clear to everyone that these types of optimization problems are everywhere, both in science and engineering. And the point is that many of these optimization problems, again, that can cover a wide range of topics like scheduling, logistics, or cryptography. They are typically NP-hard in the sense that we don't have any classical algorithm that is efficient for solving them. And this means that finding their solution becomes...
Uno sgranate di nuovo.
Again.
Now it's better. Maybe it just... Did you do something or just
No,
time?
I didn't do anything.
Okay, it's just the connection that jumps.
Wow. I'm very sorry for that. I mean, yeah.
It's fine.
So, so the idea is that those problems are hard to solve. We have no efficient algorithm, classical algorithm to solve them. And most recently, there's an interest in trying to solve them with quantum methods, quantum approaches. But typically, this involves writing this type of problems in terms of some kind of Hamiltonian. At this point, they become amenable to quantum computers, and what we're going to do today is instead is to try to solve them using tensor network approaches. Here, I named them quantum-inspired approaches, but yes, probably tensor networks is more appropriate. And the idea is that we have been working on this in the past few years, and these are some of the works that have been done in these on these topics, and I will mainly talk about the first three of them. The other thing is that works are done using our library, our tensor network library, Quantum T, that you can access and download and play with it. There are many branches. We are going to use basically just the branches that involve many-body calculations and specifically Gaussian search. But in case you're interested, we have a quantum circuit emulator, and we are developing a tensor network machine learning branch that is called CHI-T. And I'm not talking about this today, but it's related to the last topic. We also developed a quantum compiler that is called Vulcano. This is just to tell you what we do also on the development side. So let's first start from the beginning. And as I said, the question in this first part is how to obtain an Hamiltonian formulation of a certain optimization problem. And so first we start from what is an optimization problem. So basically you are given a function f that is your cost function. You want to minimize or maximize such a cost function. But you are, the point is that there are a set of constraints that you want to satisfy, and these constraints constrain the solution space. So the idea is that you are looking for the global minimizer x opt. These x opt belong to, to those bit strings that satisfy the constraint set. And you're looking again for the global minimizer of a certain function f. So there is typically a hierarchy of ways to define optimization problems from linear programming to quadratic programming and more general types of definition of your optimization problem. Here on the right, here you see, a typical example of a quadratic program where the function that you want to minimize is quadratic, f of x, and the set of constraints that you need to consider are linear and are either equations or inequalities. And the idea, again, you need to look for the minimum of this function. You need to find the set of bit string that satisfies, that minimizes this function f. Great. So what practically you do on when you want to do with when you typically want to solve these types of problems on quantum computers or for us on tensor networks, you start from a definition of the problem in terms of quadratic linear program or linear program, the one that you have on the left, and you really typically what you do is you get rid of those constraints and you define a new version of the function that you want to minimize, so your objective function here, that includes both the equality and the inequality constraints as penalties. So this is not free, and this comes at the cost of including penalty weights, here lambda m's and mu al's. So you need to actually define and tune them accordingly. And on top of that, since you are dealing also with, in general, since you're also dealing with inequalities, you also need to include more binaries, so-called slack binaries. Basically, what you actually do is transforming your inequality constraints into inequality constraints, and this costs you it costs something in terms of the binary variables that you need to include. So this way, this is actually not a very convenient way to solve the problem from, let's say, from the point of view of the classic of the way you treat constraint, but it's actually the most practical. It's a practical way to deal with constraints and to end up with a formulation that you can actually put on a quantum computer or on a formulation that you can actually tackle with with our other methods. So in the end, basically, you started from a constrained problem, and you end up in an unconstrained formulation of the same problem. This, in general, this unconstrained formulation, also known as cubo, when the variables that you are actually using are binaries, this formulation is in general NP-hard. So being NP-hard, anyway, we have classical approaches that are able to solve these types of problem exactly up to, a certain number of variables that can vary from in the hundreds, let's say, but really depends on the type of instance that you are gonna use, that you are gonna solve. And you have definitely many heuristics, and those heuristics allows you to really tackle problems in the size of 10 to the 5th, 10 to the 6th variable, so in general. And those techniques are typically based, the most general ones are based on variations of simulated annealing. Okay. So the idea is that once you have this Kubo formulation, it's easy to look at the Kubo formulation as a spin-glass Hamiltonian. You just treat your binaries as spin variables, and you just rewrite the Kubo problem by doing these substitutions. So you end up with a classical Hamiltonian These are just, you promote these variable, these sigma-2 operators. So in the end, you end up with a diagonal, a sigma z, a classical Hamiltonian that contains only sigma z terms, and that an Hamiltonian that has only, let's say, quadratic terms and linear terms in sigma z. And at this point, we know how to solve this. So basically, at this point, we mapped the original optimization problem into the solution, so meaning into the search for the ground state of a classical Hamiltonian, this h of sigma. And what we do is actually performing this search using tensor network techniques. So this practically means that you have an ansatz for the wave function that is a tensor network ansatz for the wave function. You have you express the Hamiltonian in terms of a tensor network operator, and in this case, what we do is we perform a variational ground state search with tensor network, and when the tensor network that you are actually optimizing variationally is converged well enough, you can sample bit strings from that tensor network that in general will have a bond dimension larger than 1. I will explain these details in the next slides. And you sample bit strings from that tensor network, and those bit strings, in the end, if your tensor network is well converged, your most probable bit strings will be actually the solution of the original optimization problem. Questions so far?
I guess I have a question. Maybe it's from not understanding tensor networks well enough.
Okay.
But if it's a classical Hamiltonian, aren't there classical algorithms that would perform better? Because we don't expect much entanglement, no?
Yeah, of course you don't expect entanglement. You don't expect the solution to be entangled, okay? The solution is a bit string. And that's, but the point is that getting to that solution is, in getting the procedure, the process that gets you to that solution is the one where you actually would like to take advantage of tensor networks in the sense of working with a superposition of bit strings. That's why I'm saying the whole point of this is looking for the ground state of this true classical Hamiltonian, not by just looking at the bit string that has, that is a classical state, but by looking at a superposition of states whose energy is close enough to the energy that you want to reach.
And this is better than the, let's say, a Monte Carlo algorithm for just randomly flipping screens with Boltzmann weight.
No, okay, of course you can do that. Okay, I have to say, so first of all, you will see later on that we don't do exactly we don't use just this H, this classical H, but we also use a transverse field that does not commute with the Hamiltonian. So we make this Hamiltonian with this classical Hamiltonian a quantum one. And in my perspective, this really depends. The comparison with Monte Carlo is the one that you need to do. I agree. But it really depends on the type of problem. To my perspective, the power of using a tensor network approach instead of a Monte Carlo approach is that in a tensor network you can encode many states, many bit strings. Whereas in your Monte Carlo approach, you need to sample every time. So there are problems in which this is more advantageous. I'm not saying right now that the problem that I'm showing here, so the optimization problem is one example of this. So on this, I agree with you. This may not be. Okay.
Makes sense. Thank you.
You're welcome. Okay. So just, I don't know if this is useful, but I mean, this is just a brief introduction to what is a tensor network. So the idea is that these tensor networks are a linear algebra tool designed to address high-dimensional problems, and the way they do it is by decomposing them into smaller problems that instead can be handled efficiently. In principle, and also in practice for many purposes. But okay, the idea is that those types of methods are very effective for many-body systems. And the idea is that in many-body systems, you start from an exponentially large wave function, the one that you have on the left. This wave function is represented by a tensor, and this tensor, in principle, has d to the n, is described by d to the n parameters. And each of the, this many-body system has n subsystems, and each subsystem has a size, as I mentioned, d. Yeah. So the idea is that instead of representing this tensor, you actually represent you actually end up with a representation of the wave function in terms of a polynomial number of smaller tensors. And in doing, we'll see next slide how you build that in a small example. And the way you the main parameter that you are going to tune, the main parameter that actually describes your ansatz is the so-called bond dimension that describes the dimensions of these links here. And it goes from 1, and when your bond dimension is set to 1, you have a product state. You are describing practically a product state. To, in the case of use, you use the exact bond dimension without cutting any correlation, you end up with the exact representation of your quantum state. So let's see these. Let's see in practice what does this mean. Let's see in practice how do you obtain a tensor network representation starting from a full quantum state. So this is your initial quantum state, as I said before. So it is represented by a rank n tensor psi. And what you can do is actually reshaping this tensor in a matrix with two indices, I1 and alpha. Alpha is a collective index that describes all the subsystems from I2 to IN. And at this point, you can perform a singular value decomposition, and you end up with a representation in terms with a representation of the matrix psi I1 alpha in terms of this product, where the sigma matrix here is the matrix of the singular values. So if you don't do any approximation, these that you see here in green are the sizes of each of the links in your tensor networks. But you can, for instance, decide to represent this state with, while considering less singular values. For instance, while considering only the m most relevant singular values. And this is what I mean by cutting your, cutting, or let's say having a different representation of your quantum correlations. So at this point, you can actually regroup these elements this way. So the first one on the left becomes the first element of your MPS, of your matrix product state. And you see here, I mean, in an MPS, each, I mean, when you are in the middle of your MPS, each tensor has three indices, three legs, as you can see. And you can group the others on the right. And at this point, you can keep on applying the same decomposition to the tensor psi prime. And by iterating this, you obtain a representation of the original state in terms of a matrix product state instead, where you can tune the size of these indexes, of these bonds here. So you can tune the bond dimension. And this means tuning the way you represent the quantum correlations in your system. So this is how you treat a state. This is, I mean, there are, of course, different ways to decompose the original tensor psi and to construct a tensor network ansathes. And these different ways correspond to the different tensor network ansathes. I just showed an example of the case of a matrix product state. The other ingredient that we need to look at, what we are going, at the results for the next parts, actually is how do you perform the ground state search. So the idea is that if you were to deal with the many-body state and a certain operator H, looking for the lowest eigenstate actually requires a global optimization of all the parameters in your wave function, and this global optimization, has a complexity that grows exponentially with the system size. However, if you have a representation of the wave function as a matrix product state and representation of the operator in terms of a matrix product operator, so the same type of representation also for the operator, basically you can cast the optimization, you can reduce the optimization into a series of local optimization for each tensor I. And you can sweep over I, and this goes, this just goes with the size of the system. So this is why it's more efficient to do this ground state search with this approach. Okay. So at this point, I'm gonna show some examples. The first is, unless you have questions, of course, and otherwise I can move on. Okay. So the first example of optimization problem is actually a scheduling problem for satellites. So the idea is that you are given a number n of satellites that needs to acquire images of the Earth. M images of the Earth in a certain time frame, and they can do this only, each satellite can acquire an image only in certain so-called data take opportunities. And since those images are big, let's say, they can collect a few of them and then they have to download them to a certain ground station here. And they can do this downloading procedure only in certain downlink opportunities, let's say. But aside of the technicalities of the problem, we have a mathematical formulation of the problem of our cost function f, and the main things to notice here is that we have two types of binary variables that define a problem, x and y. And each variable actually tells, the variable x tells you that the satellite I takes a certain image of the Earth j at the data take opportunities k, And Y takes care of the downlink part, so the satellite I downloads the image J at a certain downlink opportunities R. So all the others are parameter, that define the instance that you want to solve. And the important thing is that, as you can see from here, this is a linear problem. Is into different types of variables. This defines your cost function, but apart from that, you have many constraints. You have you are given 7 types of constraint, and each type has many constraints per se. So the idea is that, if you sum them up, these are hundreds of constraints, and you can see they all appear in the form that we have just seen before, so equalities or inequalities. So in the end, we have a Kubo formulation. We end up with a Kubo formulation of the problem, and again, each binary variables is mapped into a qubit. You can actually work a bit and reducing the number of binaries that are required because, again, since you have many inequalities, those inequalities brings you slack variables, and so you want to reduce them as much as possible, so you can do this a bit. And it is just on the left, you see how a typical Kubo looks like for a simple, for a small case where you have just 3 satellites and 3 targets. And we solved this problem on real instances, and those real instances are provided by the company Thales Selenium Space. And the important thing to notice here is that, let's see. First of all, the minimum size problem is 10 to 10 cube variables, minimum in the sense that it's still a problem that is interesting to solve for them, but full size problems are in the order of 10 to the 6 variables. And what we did here was actually to compare to validate all the tensor network pipeline against the classical solvers that are of 2 types, IBM and Ciplex and Gurobi. Let's see why they differ from each other. So, so the difference here is that Ciplex is, what I said some slides before, is an exact solver. So whenever Ciplex gives you a solution, the solution is exact. And the reason because it's exact is because here we are solving the integer programming version of the problem. So constraints are actually used to solve the problem. They are not included as penalty and so on, so you solve the integer programming version. And you use branch and bound technique. So basically, if your result converge, you know for sure that the solution is exact. Otherwise, it doesn't converge. The other solver that we use is Gurobi, that actually provides you with we use it actually to solve the Kubo formulation of the problem. So IBM solves the integer programming formulation, and Gurobi solves the Kubo formulation. And what Gurobi implements, I think, for the Kubo formulation is some kind of annealing procedure. So some kind of Monte Carlo. And what we have is, what we look at here is the relative mission cost. So how far we are from the correct result. So the correct result actually is the maroon dashed line, and we know this because we solved this with Ciplex, and Ciplex gave us the correct result since it converged. And you can see here that if you look at the black square is Gurobi, and at the moment with this formulation, even Gurobi with 128 variables cannot reach the correct result. The correct mission cost. And these are the tensor networks. This is the tensor network part instead. It's true that the relative emission cost is not, let's say, correct. However, the solution quality is very high. I mean, the number of constraints that are violated, here you see the number of constraints that are satisfied, and this number is larger than 99.9%. So what we did to actually did something better with respect to this result were two things. So first of all, was tuning the lambda in our formulation. So the lambdas are those that the lambdas that you need to introduce to define to include the constraint as penalty functions. So we tune them appropriately. Appropriately mean, we have automatized the procedure of tuning the lambda, and also we had a quantum perturbation in the original expression for the Hamiltonian. And by adding this quantum perturbation, of course, you need to set how big this is. So you need to set the coefficients that defines how big is your perturbation. And this tuning at the moment is not automatic. But you can see from here that, first of all, with the right lambdas, so if you are able to incorporate your penalties the right way, Gurobi finds the correct solution. Even, Gurobi used to solve the Kubo formulation, it finds the correct solution. So this means that your Kubo formulation is correct. And also up to 128, we can also converge the tensor network solution to the correct one. And so just to conclude this part, we have we found two ways to improve our results, meaning including a transversal perturbation and introducing a procedure that automatically tune the penalty weights. There are other things that can actually reduce the number the size of your problem. That is, for instance, to encode the constraints in the tensor network structure. We did this a bit. And this means that you no longer work with qubits, but you work with higher local dimensions. And those states that appear in your tensor network basically are those that already satisfy some constraints. And this is a possible way to actually solve this problem more efficiently. Okay, this was a first example. Okay, the other one, I think I'm going to be faster on this. So, as I said, first of all, there are questions, or can I move?
I guess I'm a bit curious about whether there is some physical intuition, or what is some simple way to understand why adding these quantum terms would improve the method in general.
Okay, I mean, my intuition here is the problem in these combinatorial problems, and it is also a problem for simulated annealing, of course, is that you get trapped in local minimum. Okay, so the reason you cannot solve correctly the problem is because you really you get stuck. And the idea is that if you make your Hamiltonian a quantum Hamiltonian, then your ground state, then you will have, you will necessarily have a superposition of bit strings. So this is why we decided to include a transverse field, because that way your Hamiltonian, again, is no longer classical. So you can explore a bit more, you can have a tensor network that has a finite bond dimension. That is the tensor network that represents the ground state of your final Hamiltonian. The problem that we are experiencing now is that whenever you need to look for the proper ground state, it's, I mean, the problem is how to tune that transverse field in a way that allows you to explore more local minima, let's say. So what we are doing right now is trying to set an adaptive DMRG. So try to tune that field adaptively during the DMRG procedure. I don't know if this answered your question.
Yeah, makes sense.
The problem that I'm showing here instead is slightly different in the sense that, so in here, okay, I have 15 minutes more or less, exactly. Okay. So here the problem is solving the integer factorization problem. Okay, this problem is hard. The best algorithm that we know to solve this is general number field sieve. And the idea of all these algorithms, these are all sieving algorithms. The idea of all the sieving algorithm is that if you are given an integer n, you can, this integer n is by definition odd, and you can always write this as the difference between two squares. And the point is that how do you construct these squares? Those squares, first of all, need to satisfy this congruence relation. So solving the integer factorization problem via sieving methods means searching for congruence relations. So what we did was actually trying to develop, trying to improve, on another sieving method that is not the one the one of the general number field sieve, but it's the Schnorr approach, the Schnorr sieving approach. I will give you an idea here, and I will not enter the mathematical details, but if you are interested, we can discuss this. It's just that it's a bit too long to be described now. So the idea of Schnorr is mapping the integer factorization problem into the solution of a series of optimization problems that specifically are defined on a lattice, lambda, and on a target. So the lattice and the target depends on the number n that you want to factorize are actually defined on that. And the size of the lattice depends on the size of the number that you want to factorize, and the same goes for the target. So the closest vector problem is the problem of finding the closest point in a lattice to a target T that does not belong to the lattice. This is an incomplete problem. It's hard to solve, but there is a classical algorithm that provides us with an approximate solution of this problem that here we called classical B, so the orange point. So the idea is that some years ago in 2022, there was a group that put out the idea of not solving this family of closest vector problem using the classical algorithm, but starting from the approximate classical solution and construct from that solution a set of other possible solutions that are related to the first one, to the classical one by different, by different roundings, by different possible roundings. So the point is that in the end, you start from a certain definition of the lattice and the target that depends on the n, and this defines you one closest vector problem. You solve approximately the closest vector problem with a classical algorithm, and then you use that classical algorithm to build other 2 to the n possible solutions, and those possible solutions are encoded in a certain spin glass Hamiltonian. What we did was, at first, solving the spin glass Hamiltonian using our tensor network tools and extracting different possible solutions. So, extracting sampling from let's say, sampling many possible bit strings from this spin glass Hamiltonian. Then the point is that in order to factorize, you need to obtain some solutions of these Hamiltonians that satisfies a certain mathematical property that is called smoothness. Let's say that each point in the lattice identifies a number, and that number should be decomposed over a certain prime basis that has a certain length. And these are all proper. For each number, you need to check this property. If this property is satisfied, then you have a green point, and then you can combine all these green points in a way to obtain the factors P and Q. Again, the whole point, the reason because I'm showing these results to you now is because while in the previous approach, we used the tensor network to look for the ground state of a certain spin glass Hamiltonian. In this case, we use tensor network to sample states that are close enough to the ground state. We are not looking for the ground state, but we are using the tensor network to encode states that are close to the ground state. So I will skip this. Yeah. And the idea is that, okay, I guess I will skip also this part. And I will jump to the conclusions. Yeah, so this is, in my opinion, an example where tensor networks provides you with an advantage with respect to other methods. Because again, the idea here is that you need, in order for the factorization algorithm to converge, you need to find a certain amount of solutions of those Hamiltonians, of that spin glass Hamiltonian. And with a tensor network, what you do is you start from the Hamiltonian, you add a transverse field, you try to converge you try to converge your tensor network that you build variationally again. And what you get is that in the end, your tensor network encodes many solutions, many possible solutions. And it is really, an example where what is important to you is not to converge to one single solution that is the one that has a certain specified energy, but it's finding many solutions that are reasonably, where this reasonably is vague on purpose, where, again, these bit strings are reasonably close in energy to the best possible solution. And this is an example where tensor network actually provides a good advantage with respect to other cases. So I actually mostly skipped this part because I wanted to show you a different way to actually look at optimization problems. And specifically here, so in the last 10 minutes, I want to talk about these quantum algorithms for equational reasoning. And First of all, what is equational reasoning? So the idea is that you are given a symbolic expression like a string or like a quantum circuit also, or a circuit in general, and you want to understand whether some strings are equivalent under a given set of transformation rules. And the way you do it typically is using a term rewriting system. A term rewriting system is a method, a formal method where you can derive these equivalencies by applying a certain substitution. So let's look on the right, just to understand practically what I mean. So you are given a term rewriting system S that is composed of, that is defined by, an alphabet. The alphabet here consists of two letters, A and B, and by a set of rules. Here we have just two rules. A and B is equivalent to B and A, and ABA is equivalent to BBB. Okay, so what you do is you start from a word. So here we are working with strings that have the same length, okay? But it can be generalized to strings that have not the same length. So you start from BBAA, and then you start applying these rules. And this way, you can, and by applying these rules iteratively, repeatedly, what you obtain is the class of all strings with 4 letters and 2 characters in your alphabet that are equivalent to the initial one. So typically then, when you have classical algorithms that do this, that solves this type of problem, what they require is a sequential exploration of the graph, and the graph represents here the equivalence class, so the class of the equivalent strings. And the point is that these graphs can be exponentially large. So the graph exploration, if the graph exploration is sequential, of course, it is not very convenient. So what we thought is, okay, but why can't we encode those equivalence classes into a quantum superposition and then manipulate the entire equivalence class as a single quantum state? The answer is yes. I will show in the next slide what we do. And which problems can you solve doing this? For instance, you can solve exactly the word problem. So you are given 2 strings and a set of rules, and you want to establish whether these two strings are equivalent under that set of rules. Or you can count how big is the class, how big is the set of strings that is equivalent to a certain string A under a given set of rules. And we use this to compute, for instance, how many closed path curves you can have in a 2-dimensional lattice, also known as Hamiltonian walks. Or you can also phrase some optimization problems in this way. Specifically, you can rephrase optimization problems with equational constraints. Let me give you an...
Yeah. I have some problem visualizing the slide.
Oh, okay.
Can you rephrase the last part of the speech?
Let me... how is it now?
I cannot see.
Same?
Kind of the same.
Okay, what can I do?
I don't know. I guess you can repeat the last part of the speech.
Okay. So in the last part, I was just trying to give you an idea of which kind of problem you can solve with this approach. So the approach is, since when you need to solve these equational reasoning problems, typically you need to explore sequentially the graph of, in this case, of strings that compose your equivalence class. Our idea was to try to construct a superposition states that contain the elements of the equivalence class in a way that you can manipulate each equivalence class as a quantum state. And the idea is that by doing this, you can, with equational reasoning, you can solve many problems. One is, again, the word problem, but the last one I was mentioning is actually an optimization problem where you also have an equational constraint. For instance, let's assume that let's consider the case of compilation. Compilation is an example of optimization problems with an equational constraint. Why? Because typically in compilation, you want to minimize a certain function f. That function is a function that depends, for instance, on the quantum hardware or on some properties of the quantum hardware that you are describing. The symbolic expression here, the string, actually represents a circuit, and the circuit has a property. Each circuit has a property. The property is that you want to find, it's a unitary, and you want to find another unitary that is equivalent to the initial one, the one that you are providing, but that unitary that you are looking for minimizes a certain cost function. That is the cost function that you want to minimize for your compilation. So this is just an example of a problem that requires equational constraint that you can solve actually with this approach. How is this slide? Can you see this?
Yes. Okay, thank you.
Okay. So, yeah, I will briefly sketch how you can actually build a quantum state out of an equivalence class. And the idea is that if you are given an alphabet, then you can map any string into the computational basis state of a certain qubit system. So each qubit has D levels that each corresponding to your alphabet characters, and you can construct the computational state W this way, really. Of course, any quantum state can represent superposition of strings. And the rewriting rules that we were looking at before and also are here, these rewriting rules can be mapped into operators, and these operators act locally on each qubit. Okay. So the idea is that the equivalent class can be represented by an equally weighted superposition of equivalent strings. And those strings are those strings that form the equivalence class. And we call this state an orbit state. So let's take the example that we did before. So we have just two letters, A and B, and we have strings of 4 characters, and these on top are the rules. So whenever you are given these rules in this setting, and you look at the configuration space, the configuration space is actually composed by 3 disjoint subgraphs. The green, the yellow, orangish, and the blue one, and these 3 are 3 distinct equivalence classes. Okay. So the point is, once we have defined the equivalence class as an orbit state, in order to use a quantum algorithm, we need to know how to prepare that quantum state, no? And okay, this is how we do it. So the first thing to notice is that, as I said, the rules that defines your turn the writing system actually defines a disconnected graph. Okay. But if we look at each orbit state, so if we look at each equivalent class, so each orbit state is the flattest complex function defined over a connected component. And you can use this definition to realize that the parent Hamiltonian that will define your orbit state is provided by the discrete Laplacian of the graph. And the discrete Laplacian of the graph is composed is obtained by summing all the Laplacians derived from each rules. So basically, if you want to construct the Hamiltonian, if you want to construct the orbit state, your orbit state, you need to define the Laplacian of this graph, and the ground state of this graph will correspond to the orbit. The ground state of this Laplacian, will correspond to the orbit state. In this case, we have 3 orbit states, and in those 3 orbit states are degenerate. So the trick that you can use to build a certain orbit state, for instance, the orbit state for the green equivalence class, is interpolating the Laplacian with a projector, and the projector is in this case, a word in the equivalence class that you are interested in. And so by doing a quantum annealing and using an Hamiltonian that interpolates between the Laplacian and this projector, you can remove the ground state degeneracy and you can prepare the selected orbit state. In this case, the orbit state that corresponds to this green class, equivalence class. Okay, final step, and then I'm done. So, what do we do? Then what do we do once we have built this orbit state? Yeah, once we have built this orbit state, we can actually solve the problem that we were talking about. So either, for instance, the word problem or the counting problem. So the word problem, again, is I give you 2 strings, I give you a set of rules, and we need to check whether these 2 strings are equivalent under those rules. And practically, what we can do in this framework is we can build the orbit state from the word WA. We can build the orbit state from the word WB, from the second word. If those words belong to the same equivalence class, then this fidelity will be 1. Otherwise, if they belong to different classes, equivalence classes, the fidelity will be 0. And let's look at this. I mean, this is exactly the fidelity for, here we implemented all this framework with tensor networks. So, but here the thing that I just want to show you is that if you consider words with increasing length from 10 to 100, you can see that, and you construct those words in a way that you already know which words are connected and which words are not, and you clearly can separate the fidelity of those words that are connected, so the squares, from the fidelities of words that are not connected. And it is a first result, so the algorithm does what we expect it to do. And the other problem that I want to briefly show is the counting problem. So we can count how many strings belong to a certain equivalent class. simply by computing the fidelity between the states that contain all the strings and the orbit state that contains the initial word, WA, from which you construct the equivalence class. So by doing the fidelity, by computing these fidelities, you can actually compute the size of